Go.
Hi, good afternoon, class. Welcome back to RBTC 2339 Robotics. Today we're going to go over robot frames. Our objectives today are understanding the Cartesian coordinate system, understanding, an overview of world frame and tool, tool frame, and user frame. We're also going to do an understanding of the position menu and how the location and orientation is measured. And after we're finished, you should know how to jog in the different jog coordinates. Okay? Alright, so let me ask the question and I'll give you the answer right here. Why do we need frames? Well, we need frames because frames are used to define the location and the orientation. And I know we've gone over before location and orientation, right? Location being the big X, Y, and Z. Orientation being the little X, Y, and Z. Okay? The rotations. But it is important to understand what frames are being used. So you will know where the robot will move for any given command. The times that we've been in the lab, what have we been working in world frame. Okay? And I'm going to go over back over and we're going to review world frame here and in the Cartesian coordinate system. So the Cartesian coordinate system is used to describe the location and the orientation of a position. There are two axes that are required to reach any point on the plane. That's our X and our Y. Okay, you have to think of it as a grid, right? You have a grid where you have your X and your Y, and you learn this in math. You go out so many millimeters to the X, you go up so many millimeters to the right. That is going to be part of your Cartesian coordinate system. But then we're going to add a section to that. We're going to add the Z. The Z is up and down. Now we make it a cube, don't we? Instead of just a flat plane, we're making it now a three-dimensional Cartesian coordinate system where we have three axes that are required to reach this point, X, Y, and now we've added Z. X is going to be the forward and backward in Cartesian. The Y is going to move side to side. And our Z will be moving up and down. When we have all three of these points, that is what defines our location. The big X, the big Y, and the big Z. All right, in the Cartesian coordinate system, the location is the distance in the X, Y, Z directions from the origin of the reference frame. Okay, where is our origin for world frame? Anybody remember?
In the back of the robot.
Okay, Leo, in the back of the robot. We face behind the robot and we do our right hand rule of thumb. The orientation is the rotation about the X, Y, and the Z axes of the reference frame. So, we talk about X, Y, and Z, the small one. In Cartesian, can anybody tell me what that's called, the rotational? Eli, you know it. The small X, Y, Z in Cartesian, what do we remember that by?
Yaw, pitch, roll?
Yaw, pitch, and roll. Okay? The yaw, pitch, and roll. So when we record the position, its location and orientation is automatically recorded as X, Y, Z, yaw, pitch, roll relative to the origin of the frame it uses as a reference. Now, before I kept saying, as we get to world frame, as we do world frame, now we're going to learn more frames other than the world frame. So I have to address it this way, that it's relative to what origin of the frame that we're going to be referencing it to. So with that being said, we have 5 methods of jogging. 2 of those are already defined. Can you remember what they are? It's on the PowerPoint. Joint, which is your non-Cartesian, and world. Okay? Now we're going to talk about 3 other ones, and only focus on 2. We're going to talk about the tool frame, and we're going to talk about the user frame. And the other one that we can use is called the jog frame. I'm not going to focus on jog frame at this moment, but we will discuss it later in another lesson. So the types of frames / Cartesian coordinates, this is some information about it. A frame is an intersection of the three planes at right angles to each other. The point where all three planes intersect is called the origin point. Remember that, origin point, because you're going to have to use this in your lab when we go to define our user and tool frames. Any point can be located within a frame by providing three positive or negative numbers to represent the x, y, and z distances from that origin. The kind of system is called a Cartesian coordinate system. One of the benefits of defining frames is to establish reference points on the workpieces such as fixture or pallet. Let me explain that a little differently in manufacturing terms. All right, we have the assembly line, okay? And on that assembly line, we have a robot that has to do something, all right? We have a frame that is designated and defined for that robot to operate, okay? And it has a certain tool on it. And when you have a certain tool, you have to define that tool frame, and you also have to define that work area specific to what you want to do. Again, world frame has a different location of origin, where your user frame would have an origin point where that you define that frame. Okay, so don't lose count of that as we move forward. When working, when the work pieces moves, then the program can be edited by adjusting the frame rather than adjusting all positions, positional data in each program. So it does benefit using user frames, because if I have to move my frame, okay, or I get something that's different, that we get a modification, instead of having to go through and change all of our points, right? But our user frame, say our jig, got moved 2 centimeters or 2 inches this way. Well, we can now do offsets in our program to make that happen, so we don't have to go in and change every single one and touch up every single data, okay? And so that's one of the benefits of having user frames. All right, next. World frame. Now, we've already discussed world frame when we dealt with learning our coordinate systems. Okay, so again, this is a review. World frame. Frames are used to describe the location and the orientation of the position. We discussed that. When recording the positional data for a program, and no frame tool center point, and we're going to get into that here in a minute with our tool frame, and we're going to learn what tool center point is and what it means. The default location of the TCP is the center of the faceplate. So if we don't have a tool on it in our end of arm tooling, we use our faceplate as our TCP, tool center point. Okay? Once we add a tool, then we have to change that tool center point, and that's where we begin to define our tool frame. The TCP location can be changed once tooling has been added to the robot. When recording the positional data for a program, the robot measured from the world origin to the tooling is represented again as a new XYZ and yaw, pitch, and roll. The world frame is a default frame of the robot. It cannot be changed by the user. Remember, it cannot be changed. Okay? The origin of the world frame is located on the center of J1 axis and the height of the center of the J2 axis. And in the next slide, I'm going to show that where it is on our particular robot out there. The location of the origin never changes in world. Okay? It never changes in world. And the orientation of the world frame never changes. When jogging in world, the servo motors will maintain a linear, otherwise known as a straight movement. So in this one right here, this is our robot in the lab. Okay, it's the LR Mate 200 actually it's the IA4. Okay, but it looks the same as this. It's just this with a bigger one. What we have here is you're going to notice that it's the center of this joint right here. Okay, this is joint 2, right? Joint 1 being down here, but it's the center in there along this perpendicular of joint 2. Okay, remember before where I showed you on the other robot in the lessons prior to this, I had another type of robot up there. So we had the servo motors going across. Well, here obviously you can see they're inside. So that is going to be how you determine your origin or the world frame. Any questions on that so far? Okay, let's move forward. The directions of the world frame can be represented by the right-hand rule of thumb. We did this last time, right? Everybody put up your right-hand rule of thumb. Okay, also in world coordinates can be better understood if you stand behind the robot or by the side of the robot using the right-hand rule of thumb. Okay, X being this way, moving forward and backward, Y moving side to side, and Z moving up and down. In a linear motion now because we're in world mode using the world Cartesian coordinate system. How does that differ with joint? Anyone tell me?
Joint controls each axis individually.
Very good, all right. Very good. Okay, the type of motion achieved when selecting a world jog frame is a linear motion. This means that any end of arm tooling mounted on the robot will move in a straight line. Movements while in world are based on the Cartesian X, Y, and Z coordinate system. The robot will move several axes simultaneously to maintain linear motion to reach a designated point in space. So when we were in joint mode, we were moving individually, each joint, to get to where we want to go. Once we learned about how the world frame works, and knowing that it works in a linear motion instead of a arc motion, because our joints run on a degree, where our world Cartesian system runs on a linear, and then it turns into millimeters. Okay? When precision is necessary while jogging, world is the jog mode to select. So if we want precision, we want to be in world jog mode, because that will give us our best method of getting to a position where we need to be. All right, finding our position and where we're at. We use the position screen to display the positional information either in joint or in Cartesian coordinates. You can see on the screen where we are when we do our position menu. The positional information on the screen is updated continuously when the robot moves. So you can actually be in this and you can see the robot moving. Okay, as it moves, you can see the numbers change. The information displayed on these screens is for display only. You cannot change these. Where can you change the information on position? Where have we discovered that? Anybody? Where do you go every time you shut down?
Home position.
Okay, is that where we can see our positional registered positional data?
Yes.
Yes, we can. We have that position button there. It's a soft key. But we can change that one, okay, because we're in a positional, we're making an input to that. We cannot change these. These are just a status information, okay? There's no changing that. All right, let's talk about the different positional status positions data that is represented and what they are, their unit of measurement is. Okay, first we have joint. Okay, the joint screen displays the positional information in degrees for each robot. Oops, I'm sorry, right there. The tool indicates the number of the active tool frame. All right, so we're going to be when we look at the screen, I believe we can look back at it. If you look right here, see this right here? Okay, this tells you that it's tool number 1. That means you're using tool frame number 1, okay? And you are in world, the world position, and so these are going to give you readouts in millimeters, okay? If we were in joint, this would be highlighted, and these would be written in degrees. Make sense?
Right, sir.
Okay. Moving forward, we can go to the next one, which is the user. The user information. The user screen displays the positional information in Cartesian coordinates based on the user frame. Okay, this is one that we're going to define, not one that's already defined. We're going to define our own user frames, and then once we get there, we can click on to the soft key to user, and it'll show what our data, positional information data is according to the user frame origin, point of origin. Does that make any sense? Am I confusing anybody here? Hope not. Okay, joint reads in degrees, right? And then, so when it comes to the world, we're reading it in a default mode, right? And our point of origin is where? Behind the robot. Okay? So that's where our 0 is. And we move outward this many millimeters. We move side to side this many millimeters, or up and down this many millimeters. When we're in user, we have defined that frame already. So what we're doing now is we're taking it off of that point of origin that we defined in our user frame. And so when we read that positional data, we're reading it according to what our user frame is. Okay? I know it sounds a little mumble-jumbled right now. You're a little probably confused. Once we get into user frame and how it works, you'll understand it a lot better. Okay? And then we have the next one, which is our world. Did we do world? We did. Okay. World being that it is the informational from the world standpoint. Now, moving forward, this is how we get to our position key. We can either press the position key, and that brings up our screen, and the position key is on the teach pendant, right? This screen comes up. This next step is that we select the appropriate coordinate by using our soft key, whether it be joint, world, or user. Or joint, user, or world. F2 being joint, F3 being user, and F4 being world. We can also do this. How else can we do it? Can we get to the positional data? Anybody? Just give me the first key.
Position.
Anybody remember? So you remember the little 3 keys that are there? Go select and edit and
Data.
data. Okay? Now, what's right next to that?
Motion.
No, that's not that way. What's this way?
Menu.
Menu. And use a menu key. Right? Okay. Okay, let's talk about this part. Tool frame. You ready to get into tool frame?
Yes, sir. Yes, sir.
Alright, we've covered world frame. We understand how this Cartesian coordinate system works. Now let's start working on our tool frame. Tool frame is an important reason to define our tool center point is simply to jog the TCP to the workpiece, which makes programming easier. Some software applications are based on the correctly defined TCP, and a tool frame allows you to control the robot based on your tooling, not based on your robot now. Okay? Understanding that we have to set a tool frame, so we need to define what our tool is, what our measurements of that tool is, and how it's going to work in our programming. Another important reason to define the TCP is to have consistency from robot to robot, especially in a plant that has many cells. By default, the TCP is the center of the robot's faceplate. I mentioned that before. This is the tool origin or tool 0 location. Okay, so now we have a tool origin. Back here, if you see this, you can see here that this is without a tool. Okay, so your origin right here shows this angle, a vector, but when we come over here and we add a tool to it, now we have a whole different vector here, which changes our position location as it vectors, and now our center point for our tool is not here anymore at the faceplate, it's at the end of the tool. Okay? And we're going to go through that here in just a minute. Alright, coming back to this screen. When you set up a tool frame, it's also called a U-tool. You move the TCP from the robot's faceplate to define the point on the applicator, the gun, the torch, or any other tool where you'll be painting, welding, sealing, handling, or any other application work that is done. So, paint department has paint guns, right? Okay, body weld's got all kinds of stuff. They've got MIG welders, they've got spot welders, they've got seal applicators, okay? They've got multiple different size spot welders, okay? All of those are going to have a different TCP. So we have to define that TCP and create our tool frame. Here are some examples of tool framing and using our TCP. In a paint tool, the TCP is approximately 12 inches from the end of the applicator. This can vary depending on the particular application. Why do you think it's 12 inches, approximately 12 inches away as your TCP? Why wouldn't it be the end of the gun? Because you're spraying outward, right? So whatever is defined as your spray out, that end of that is going to be your TCP. Okay, you can't use your tool, you can't use the end of the paint gun because then your paint gun is going to be like right next to the thing here, and you got to have that spray out position. So you got to measure what your spray out position is going to be, right? Another one would be the arc tool, and this is the TCP is going to be at the tip of the wire, because the wire is what's making the connection, not the end of the gun. Okay? I know you guys, Lucas, you work in body weld. You've seen how the MIG welders work. There's a distance between the end of the gun and the product, right? Okay, so this where the end of the gun is not your TCP. It's going to be right where that wire connects to the piece of aluminum or piece of metal that it's welded. Okay? Everybody understand that? And you have to be able to measure that, okay? I don't truly know what the distance that it is between the end of the gun and the tip of the wire. To me, it looks like maybe, I don't know, maybe a half inch, quarter inch to a half inch. But of course, it's Toyota, they go in millimeters, okay? So I'm not sure what that would be. It all depends on how it's programmed, okay? And then the next one, we have the spot welder. We've seen this plenty of times. Spot welder, the TCP, is where the tips of the gun meet when they're closed, okay? They meet when they're closed. So what you'll do is when you want to find out what that TCP is, you close the gun, and then you're going to measure from the end of the faceplate to where that is and the distance between that, and that's how you're going to determine your TCP. Yes?
Is that the same thing with the gripper that we have on the robots now?
Yep, that's going to be the same thing. I'm getting to that. See that? Look at that. Hammering tool. Same thing. Okay? It's when you close that gripper is where you find your TCP. Okay? Because that gripper could change depending on the size. Alright? Our gripper is very small, right? But the thing about it is, it comes straight through. But what else do we have inside that gripper? Anybody know? It's red. The laser. Well, the laser's not in the middle, is it? It's off to the side. Okay? So it's coming directly from the middle of that faceplate, going down, however many millimeters it is, to the end of that gripper when it's closed. Okay? So it's got to be when it's closed. Okay, methods of defining a tool frame. We have 3 different methods to define a tool frame. The first one is called the 3-point method. It defines only the location of the TCP when the values cannot be measured and directly entered. So if we don't know, say for instance we get a tool on there, we have no idea what the measurement is to where we can go and do a direct entry. We can use this 3-point method to only identify the TCP values for the location of that TCP. The X, the Y, and the Z. Remember, location is big X, Y, and Z. The other one that we add to that is the 6-point method, which is an additional 3 locations. And that is going to be the location of the orientation of the tool frame when the values cannot be measured and directly entered. So this is the lab that we're going to participate in today. Is we're going to be doing a 3-point and a 6-point method tool frame definition. Okay. The last one that we're going to talk about, and we won't be doing this, is that this direct entry method is used when tool dimensions are known and can be entered directly into tool frame settings. Direct entry must be used with 4-axis robots. So if I have a robot that just has 4 axes, okay, then I would use the direct entry. But we're using 6. We can use the 3 and the 6-point method to define our tool center point. Everybody understand how this tool center point works? If we do not have a tool on there, where is our tool center point? Center of the faceplate. Good. Okay. If we do have a tool on it, say for instance we have a paint gun on there, how do we know where our tool center point is? At the end of the spray. Okay, that's how we can describe it. Now, it's approximately 12 inches. It could be your company sprays out 5 inches to get a thicker coat. So whatever is at the end of that spray is what you determine is your TCP. Any questions over tool frame? Alright, so let's move on into our user frame. This will be the last part of this lesson, and then we'll go out and do our lab. The user frame can be set up in any location with any orientation. All positions are recorded in the user frame. If no user frame is specified, guess which one is going to be our default? World. That's correct. All positions in the user frame are recorded with respect to the origin of that frame. And we will determine what that point of origin is. Let me give you an example. This right here is user frame 0, which is the default user frame of world. Okay, this is a world user frame, taking our point of origin right here, and then measuring our positional data from this particular user frame. If we move to our user frame 1, which we have defined as our user frame, our point of origin now goes away from a robot and goes to the origin of what we want to use as our frame. Our frame could be any number of things. It could be an imaginary area that you only want to work in. Okay? It could be a jig. It could be a tabletop. It could be anything that you define as what you want for your user frame. Okay? So if I have a robot, let's just take this podium for instance. If I have a user frame here, okay, I have this podium, and I want to define the top of this as my user frame. Then I would bring my robot and do my method of defining that and making my point of origin, let's say right here, because I don't want to include this. I just want to use the flat part. I make this to my point of origin. I have to go out a certain distance this way, okay, mark that, come back to my point of origin, go this way, and that will define, that's now defining what my user frame is going to be. Everybody understand how that concept works? Okay? Taking my new point of origin away from the robot and now putting it to the user frame itself. User frame hints. These are some things you might want to understand and learn. If the origin and location of frames changes, positions change with the frame. So if we define that frame and we make changes to that, if we make changes to the frame, the positions are going to change with it. Okay? Programs taught in one user frame will not run when a different user frame is selected. Okay? You just can't do it. And it will be defined in your program what user frame you're going to be using. Okay? If you don't do a user frame, then if you don't assign a user frame, then you're going to end up being in which one? Anybody tell me? We've talked about it. What's the default? World. The world frame is your default. So if I don't define, if I don't go and do what I need to assign my user frame, then it's automatically going to be the default frame of the world. All right. The active frame can be set and changed within the program as needed. So we can do it inside our program. We can make it a line item. Okay? We can actually, in our program, in the very beginning, we can define what user frame we want to use. What does that do? That isolates your program to others. Okay? So if you assign it in your program, what it does is it changes your user frame while you're in your program. In other words, you do not have to go and change your user frame when you're running it in auto. It's going to change it for you inside your program. Okay, so if you're in user frame 17, because you have 17 different defined user frames, well, when you bring your program up and you go and you run that program, boom, it's going to automatically go in the frame it needs to. Any questions on that? Okay, another way you can do it is by manually inputting your user frame by hitting the Shift Coord key. Okay, when you hit the Shift Coord key, now you are going through and you're going to adjust your user frame and your tool frame to the assigned frame that you want to use in your particular program. Okay, while you are, one, teaching or running it through manual. Okay, that make sense? And if we do not assign a user frame within the program, in order to run that program in auto, we need to manually assign our user frame when we go to run that. And this is why it's important that we put it in our program, because we just make it happen. It just happens. Okay? Methods of defining a user frame. We have two. I think it's two. Is it two? Nope, we got three. Sorry about that. We have a 3-point method. Recording 3 points defines the user frame. The three points are the origin, a position along the x-axis positive of the user frame, and a position on the xy plane of the user frame defines the xy plane and the yz plane. Right? So let me read that again. The 3 points are the origin, a position along the positive x of the user frame, and a position on the xy plane of the user frame. That's what defines the xy plane and the yz plane. Okay? And that's where you're going to get your 3D cube looking frame. You understand? Don't worry. You'll understand when we apply it. Right now, take your notes. Just good information to have. Then we also have what's called the 4-point method. The 4-point method defines a frame that has its origin at the position other than the reference of the frame. You can also use it to define multiple frames with parallel axes. See? So they have to be parallel. The 4 points are the reference of the frame, origin point they call it. A point along the positive x-axis of the frame, the xz plane. A point along the xy plane of the frame, which is the xy plane and the xyz plane. And the origin of the frame, which would be the system origin. So this is a little more complex. Okay, but this is if you're using multiple frames. If you're just using one frame, you only need to do the 3-point method. Okay, but if we're doing some multiple frame that's parallel to each other, then we can use the 4-point method and identify that second one. The last one would be our direct entry method, and it is used when you know the coordinates of the user frame. This allows you to assign an origin with the values for x, y, z, yaw, pitch, and roll. Okay, this is where you know the information, and you can go in and just directly input it into the software. We're not going to do that. We're going to make our own frames because each one of you is going to have a different type of frame. Okay? You're going to be assigned your frame. That's pretty cool, right? And you're going to have to remember that frame because every time you go from that point on, your particular box is going to have to be in that frame all the time. Because now it's a matter of aligning your frame correctly because I have 15 of you people and then I have 10 more. Okay, and each one of you are going to be assigned your own frame where your box is going to be located. So if you decide that your box is gonna be a little bit on this side over here, you need to make sure that each time you go to do a program, that that's where your box is gonna end up being. Because that's where you're gonna assign your user frame. Okay? Any questions? No? Alright, so what we're gonna do now is we're gonna go in the lab and we're gonna define our tool frame. And we're going to define our user frame. So go ahead and take 5, and I'll meet you in the lab.